Okay, the streaming is starting. Okay, today we continue with the discussion of the processes that we may include in our ecological models. Can you hear me clearly?
Yes.
Okay, thank you. As I told you, the subdivision into categories about processes is between physical processes, chemical processes, and biological processes. Today we will start looking into how we will model physical processes. In particular, physical processes I'm thinking at are absorption and ecotoxicological processes, and the other that are dynamical processes that are mass balance, mass transport, and chemical reaction models, which will be the subject of next lecture on Thursday. Let's start by our perspective of the ecospheres, and let's give a look at what we mean by ecotoxicological processes. We know that toxic substances are found in several forms in the different spheres: lithosphere, hydrosphere, atmosphere, and biosphere. And in general, we recognize that spheres can be in equilibrium with each other, or dynamic, or there may be some kind of dynamic phenomenon, or a dynamic phenomenon of exchange that can take place. And in that case, we may talk about dynamic equilibrium of the spheres. So it is a matter of finding equilibrium points or equilibrium concentration or equilibrium flows in order to describe the condition of static dynamical equilibrium. First of all, in order to discuss about ecotoxicological processes, we shall give some definitions. We talk about bioaccumulation in air, water, soil, or food. Bioaccumulation is made up of two sub-processes. First one is bioconcentration, when we talk about transfer of a toxic substance from water to another media, to another medium. So bioconcentration is the process of transferring some substance, toxic substance that is dissolved in water, into other media. On the contrary, the second process that happens in bioaccumulation is called biomagnification. Typically, this is what happening in food webs. Biomagnification is the increase in concentration of a substance due to the transfer of this substance through processes where different from processes of concentration. So typically, transfer of substances through, for example, food webs or exchange of foods. In particular, let's give a look to the various processes we may employ to describe this kind of equilibrium. In particular, let's give a look to the equilibrium between lithosphere and hydrosphere. So the transfer of a substance between the lithosphere and the hydrosphere. You know already this process. This process is called adsorption. And now we introduce some models we may employ for describing a process of adsorption. In particular, we have four models, four general models. The first three are the Freundlich-Peterson, the Redlich-Peterson, the Freundlich, and the Langmuir isotherm. So the first three processes are isothermic processes, meaning that the temperature is not changing during the process. And the four more general process of transfer we may conceive is the partition coefficient model for describing the transfer between lithosphere and hydrosphere. These four are models that we may employ for describing the equilibrium between lithosphere and hydrosphere. So the first three refer to adsorption processes. The fourth one, but is more generic, general one, also may describe adsorption, but may also describe equilibrium dynamical exchange processes without going to much details on the processes itself, but simply employing equilibrium coefficients or partition coefficients. Let's give a look in detail to the chemical process of adsorption. We know that contaminants and pollutants, in particular pesticides, heavy metals, and so on, but also we also consider nutrients in this context as a pollutant, are found mainly in the sediment of aquatic ecosystems or in the suspended matter. You know, as ecological engineers, that many or most of these toxic substances tend to move with the solid substance. We said that these substances are moved through solid transport. Equilibrium, that is a dynamical equilibrium, is achieved very quickly, in this case, in the process of adsorption, and a steady state condition is quickly achieved. As we have anticipated, these processes are modeled using isotherms, but depends on the substance involved, the adsorbent, and the adsorbate. The adsorbent is the substance that absorbs the material, and the adsorbate is the adsorbed material. This is essentially a surface process, so the solid surface is mainly involved. And the very general model we may employ to describe this surface process is the one that I have written here. So we may say that the concentration in the adsorbed fraction, so solid concentration, Qs, is equal to an equilibrium constant K times the concentration in the liquid phase, so the water concentration Cs, divided by a parameter delta, that is a dimensionless generalization constant, plus a parameter H, that is called generally the heat of adsorption. This parameter is a derivation of the enthalpy. Enthalpy is a thermodynamic potential. It is exactly related to the exchange of heat between media, in substances, and this heat of enthalpy, or this heat of adsorption, is multiplied to liquid concentration Cs elevated to another dimensionless coefficient beta, but it is trying to describe the heterogeneity of the media, the adsorbent in particular. So this is maybe called an heterogeneity factor. So these equations, this model may be depicted, and we have essentially three flavors for these models. First one is the Redlich-Peterson isotherm, that is obtained when we set the generalization coefficient delta equal to 1. So this is the equation describing the model. Concentration in the liquid phase is equal to an equilibrium constant K times the concentration in the concentration in the solid phase is equal to a constant K with an equilibrium constant times the concentration in the liquid phase divided by 1 plus H times the concentration in the liquid phase elevated to a power beta. And this is the Redlich-Peterson isotherm. Another flavor of this adsorption models is the Langmuir isotherm. In the Langmuir isotherm, the assumption is that of homogeneous adsorbent surface. In this case, we may set the exponent of the concentration in the liquid phase beta equal to 1. And the assumption is that of a monolayer adsorption with a capacity that is exactly K divided by H. And in this case, if we put delta equal to beta equal to 1, we obtain this very simple equation Simple because, as we will see, this is a first linear differential equations. In particular, sorry, we have seen Raddick-Peterson, the Langmuir isotherm, in which the assumption is beta equal to 1, and the Freundlich isotherm. It is important to notice that in the case of the Langmuir isotherm, we may change the scales of our descriptions, and in particular, if we plot the concentration in the liquid phase divided by the concentration in the solid phase, C over S, and if we plot this ratio as a function of the concentration in the liquid phase, we generally obtain some linear models. If you put, this is a log-log scale, if you reverse the Langmuir isotherm, you can calculate the quantity concentration in the liquid phase divided by the concentration in the solid phase, and this is made dependent of the concentration in the liquid phase. In these cases, depending on the type of the absorbent element, so the element that is absorbing the toxic substance or the adsorbate, we obtain linear lines, and in particular over a wide range of concentration in the liquid phase, depending on the different adsorbent types. In particular, here we have distinguished between clay loam, and loamy sand, and we have different behaviors. For example, depending on if we fix a concentration in the liquid phase 20, if we look at, we say that the concentration in the liquid phase is 20, then depending on the type of adsorbent, you will have different ratios between the concentration in the liquid phase divided by the concentration in the solid phase. So, of course, the smaller this ratio, the bigger the concentration in the solid phase. So the smaller this ratio, this means that the substance will be mainly found on the solid phase. So we said if we fix the concentration of the liquid phase 20, then we will have a concentration, if the adsorbent is clay, we will have a concentration that is around here. If the adsorbent is clay loam or loam, the concentration, the ratio between the concentration in the liquid and the solid phase is here, while we will have growing values of this ratio, meaning that, for example, in the case of loamy sand adsorbent, we will expect to find most of the toxic substance in the solid phase. Most of the toxic substance in the solid phase when concentration S grows. So when we have smaller values of the C over S, we are expecting to find the toxic substance in the solid phase. The third isotherm is the Freundlich isotherm, but it assumes an heterogeneous adsorbent with sorption sites that are energetically non-equivalent. In this case, we set delta equal to 1, and the adsorption model becomes this one. So the concentration in the solid phase is made dependent non-linearly on the concentration of the liquid phase CS, and the dependence is calculated through two coefficients: A, the so-called layer capacity, that is the equilibrium constant divided by the enthalpy, heat of enthalpy factor H, and we set the exponent on the concentration in the liquid phase equal to 1 minus beta. In this case, we will see soon that if we pass to a log-log description, then again we may obtain on a log-log scale a linear distribution of concentration in the liquid over the concentration in the solid phase. If we make a plot of these three isotherms, these are the results. We are plotting concentration in the liquid phase against concentration in the solid phase against concentration in the liquid phase. So as the concentration in the liquid phase grows, I am expecting to find, of course, more material in the solid phase, so adsorbed. And the three models we have introduced have these shapes. Of course, this is the Redlich-Patterson, that is an unlimited growing transfer from the liquid to the solid phase. This is the Freundlich isotherm, again, continuously growing, but more slowly than the Redlich-Patterson, and displaying a kind of plafond while the concentration in the liquid phase increases. And the third, the Langmuir isotherm, displays clearly a plafond in a kind of dynamic steady state condition. Okay. If I recall you that these graphs, these processes are obtained in isothermal condition, this means that we fix the temperature, or we assume the temperature is fixed, and then we look in how material moves from the liquid phase onto the solid phase. We obtain these three types of description according to the assumptions we have made. The Redlich-Patterson and the Freundlich adsorption assume that there is not limited availability of adsorption size, while the Langmuir isotherm assumes the assumption on the basis of Langmuir isotherm is the adsorption size on the adsorbent are limited. This means that little by little the absorption sites are filled up so that the process of adsorption or of transfer from the liquid phase onto the solid phase tends to stop on a plafond. Finally, we should note that, as I told you, these graphs are made at the constant value of the temperature, so these are isothermal. From a thermodynamic point of view, these are isothermal transformations. A good question I may pose is what happens to these graphs if the temperature changes. Let's say that these graphs are obtained with a temperature T1. What happens to the graphs if the temperature increases to a T2 that is larger than T1? When I'm expecting that if the temperature increases, I will have a switch of equilibrium toward the liquid phase. This means that these curves, if the temperature increases, tends to lower. This means that the plateau or the saturation is reached more quickly at a higher temperature. I hope this is clear. Then let's go and let's give a look to a final model of transfer from the liquid to the solid phase, the so-called partition coefficient model. In this case, we assume that we start from a very general equation of absorption, isothermal for absorption. We set our parameter delta and beta equal to 0, and what we obtain is a very simple linear relationship that links the concentration in the solid phase QS to the concentration in the liquid phase through the so-called partition coefficient. This is a very general approach, as I told you. There are several ways of estimating this partition coefficient. In particular, we may made from experimental observation explicit the dependence of a partition coefficient onto two parameters, FOC, that is the fraction of the organic carbon, the weight fraction of total carbon in the solid matter, so how much organic carbon is present in the adsorbent. So this is a characteristic of the adsorbent, how much carbon, time the KOC, that is the organic carbon partition coefficient. So this coefficient describes how much is the tendency, how large is the tendency of material to move toward those media in which more organic carbon is present. Again, we may find some experimental relationships that allows us to estimate the KOC as a function of the octanol water partition coefficient KOV. Experimentally, the relationship is this one, 6.17 times 10 to the minus 7 KOV. This means that known the KOV, and the KOV is a characteristic of the substance, of the toxic substance, then we can calculate the KOC, so how much this toxic substance is friendly to organic carbon, so tends to move toward the organic carbon. Of course, this is an empirical relationship that we may find in literature. The classical values, coefficients are those that I'm writing here, 6.17 times 10 to the minus 7. If we do a log-log so of this model, then we obtain that the log of KOC is equal, we may obtain, sorry, a relationship between KOC and the KOV, but is this one, this is an exponential non-linear linkage between KOC and KOV. This allows us to estimate KOC as a function of a characteristic of a substance KOV. This relationship is determined by these two parameters, alpha and beta. And if we make a log-log of these relationships, when we obtain a linear, in a log-log plot, we obtain a linear relationship between log KOC and log KOV. What is KOV? You have already heard about this. This is the contaminants octanol water partition coefficient. So it is a characteristic of the contaminant, but tells us how much the contaminant is lipophilic. A coefficient, the KOV is a coefficient representing the ratio of the solubility of a compound in octanol, that is the prototypical non-polar solvent, to its solubility in water, but I recall you, it is the most general polar solvent we may conceive. The higher the KOV, the more non-polar the compound is. So log KOV values are generally used as relative indicators of the tendency of an organic compound to adsorb to soil. In this case, the organic compound is the adsorbate, while the adsorbent in this case is the soil. Log KOV values are generally inversely related to the aqueous solubility and directly proportional to the molecular weight of a substance. Here, graph displaying the relationship between the ratio concentration in the solid phase and concentration in the liquid phase, QS over CS, so the fraction, this is the fraction, the solid fraction that adsorbs as a function of log KOV. So we have a relationship linking characteristic of the toxic substance, that is the log KOV, to the facility to which this substance tend to move onto the solid fraction. We have some kind of sigmoidal relationships. Sigmoidals means these are curves that present an inflection point, so there is a change in the concavity. We have, for example, for weak sorbers, we have a tendency to move toward the dissolved phase, while for strong sorbers, we have a tendency to move to the particulate of the matter. Of course, these curves depends on the concentration of suspended matter. So the more we have material in the water column that is able to absorb material that is dissolved in the water body, then the quicker you will reach the saturation in the particulate forms. So, of course, for strong sorbers, you will have a more tendency to find the material in the particulate phase, while for weak sorbers, you will have a more strong tendency of a substance to be found in the dissolved phase. All these graphs may be of help for the environmental engineer who wants to understand where he shall expect to find the toxic substance more dissolved or more linked to the particulate phase, so more in the solid phase. Here I have displayed various substances. For example, this first box and whiskers plot refers to pesticides, whose median value is the one represented by this vertical line. In these boxes, you have a lot of different substances all falling inside the category. The first box here is for pesticides. This box refers to phenols. This box refers to nitrosamines and so on. And this large box refers to ethers, that are, as you know, polycyclic aromatic hydrocarbons. Starting from this modeling approach, we may extend our description in order to also evaluate the equilibrium between the other sphere. In particular, the equilibrium between the hydrosphere and the biosphere is treated or is modeled through what is called the bioconcentration factor model. What is the bioconcentration? Bioconcentration, BCF, is equal to the ratio between the concentration in the between the concentration in the biota and the concentration in water. So this value CB refers to concentration in the living organisms of a toxic substance, while CW refers to the concentration in the water column. Again, we may try to estimate the BCF by, for example, expliciting the concentration in the biota as function of the concentration in the lipid phase times the fraction, the lipidic fraction. So we are re-expressing concentration in the biota by the concentration in the lipids. This is because the toxic substances to which we normally are interested are mainly found in the lipid quota of the organic tissues. So this is why it is important to have an estimation of a concentration in the lipids. And if we multiply the concentration in the lipids to the fraction of the lipid fraction, so how much lipid tissues are present in this particular type of organic matter, we obtain the concentration in the biota CB. Is it valid for all substances? In general, no, But as a first approximation or a first assumption, we may assume that the concentration in the biota is dependent on the concentration on the lipid times the fraction of lipidic quota in the organic matter. If we put these together with the definition of KOV, we obtain for a bioconcentration factor model, a simplified model that means the bioconcentration factor dependent on the lipid fraction of the organic matter times the KOV. Again, the lipidic fraction of the organic matter is a characteristic of the adsorbent, while the KOV, again, is a characteristic of a toxic substance or of the adsorbate. So we make a linkage between bioconcentration factor through a characteristic of the adsorbent time a characteristic of the adsorbate. In general, we may rewrite this model in this way, so that if recalling you a definition of a KOA, you may write that the bioaccumulation factor or the uptake from water by plants and animals is maybe modeled as logarithm of the bioconcentration factor is equal to the logarithm of the lipid fraction plus b times the logarithm of the KOA. So if we make a ratio between concentration in the organism and concentration in water, is it exactly what we have called bioconcentration factor? And by expressing this, we may generalize this relationship that we have assumed as a first approximation valid for all substances. We may generalize this relationship by employing a parameter B that makes the bioconcentration factor dependent on the lipid fraction, characteristic of the adsorbent, times the KOV elevated to power B, and the KOV is a characteristic of the adsorbate. We may extend analogously with partial coefficient models also to describe the equilibrium between the lithosphere and the biosphere. For example, the lithosphere may be soil and sediments, and the biosphere, biota. Again, we rewrite bioconcentration factor equal to concentration in the biota divided by concentration in the liquid phase. Then we may rewrite, multiply by concentration in water, and then we make the concentration, the bioconcentration factor for the lithosphere biosphere equilibrium dependent on the bioconcentration factor for the hydrosphere lithosphere equilibrium. Sorry, for the hydrosphere biosphere equilibrium, so the BCF W divided by a factor of KD, that is somehow descriptive of the lithosphere characteristic. By inserting the definition of BCF we have found the preceding slide, we may write that the bioconcentration factor for the lithosphere biosphere equilibrium is equal to the lipid fraction in the biosphere time KOA, so characteristic of the adsorbent time a characteristic of the adsorbate, divided by a factor that describes the characteristics of the soil, so the linkage between the lithosphere and the biosphere. Characteristics of the soil are accounted to by the factor FOC, that is the fraction of the organic carbon you may find on the solid part. Again, so you make a ratio between the lipid fraction characteristic of the adsorbent times KOV elevated to B characteristic of the adsorbate divided by characteristic of the adsorbent in term instead of lipid fraction in terms of carbon fraction. So we are describing lithosphere as in terms of the content of organic carbon time again characteristic of the adsorbate KOV. So if you put all these together, you obtain that the bioconcentration factor or the equilibrium between the lithosphere and the biosphere is simply dependent on the ratio between the lipid fraction in the biosphere divided by the organic carbon content in the lithosphere, so characteristic of the biosphere divided characteristic of the lithosphere, times a characteristic of the toxic substance, so the adsorbate, elevated to a power of 0.09. If you notice, this is almost zero. This means that the dependence on the KOV for the equilibrium lithosphere biosphere is very weak. This means that the equilibrium between the lithosphere and the biosphere is essentially linked to the organic carbon content and to the lipid fraction content of organic matter, and it is less related to specific characteristic of the toxic substances. This means that in general, in the lithosphere-biosphere equilibrium, you may expect to find the toxic substance independently from its characteristics to move toward one of the matrices depending on the lipid content of organic matter or on the organic carbon content of the soil. So here we are describing how toxics tend to move from the water column onto the organic matter lipid fraction and onto the solid organic carbon content. Okay, this more or less is all the environmental engineer has to keep in mind when you want to describe ecotoxicological processes. So processes that describe the movement of a toxic substance between the various ecospheres. I recall you, we have talked here about the lithosphere, biosphere. We are talking about hydrosphere, biosphere, but finally we have been talking also about hydrosphere and lithosphere. So we start by hydrosphere, lithosphere, and then we describe equilibrium between hydrosphere, biosphere, and then lithosphere and biosphere. Okay, I assume that you have already seen elsewhere these models, but this is how we may think to employ these models in our description of the ecosystem. Okay, now we switch to a new argument that is the description of a balance, mass balance, through transport, mass transport, and chemical reaction models. Again, first of all, I recall you that the model has to choose the most appropriate spatial and temporal scale. In particular, we may decide to model to be zero-dimensional, and this is acceptable, for example, for lakes and ponds. In this case, we just assume our system as described by a single point, zero dimension, or we may decide to be a little bit more detailed by employing series of zero-dimensional assumptions. So in this case, you may subdivide your system and in portion, space and time in which you may consider uniform concentrations. we may typically this is acceptable. This is a monodimensional description that is acceptable for rivers horizontally or for lakes vertically. Then we may employ a bidimensional description that is necessary for lakes and lagoons. In this case, we may subdivide the space in slices. For example, distinguishing the verticality, and in transects for distinguish the horizontal description. And then you may become quite complicated and decide to be three-dimensional. This is typically the case in which you find yourself if you want to describe estuaries or seas. In this case, the description becomes quite complicated. You have slices in the horizontal and transects on the vertical, and across all these lines, you may consider constant values of concentrations. Of course, time depends on the processes taken into account. For example, we may assume networks that are often static, as we have seen some example. For example, the box and arrows model, in which we assume a static description or a photograph. And you may always ask yourself, or the model may always ask himself, if this is a valid approximation or not. Again, looking at the interaction between spatial and temporal scales, dependence on the type of processes, you may say that physical processes requires lower temporal scales and high resolution spatial scales, when we have chemical processes and biological processes for which these two scales may increase. So chemical processes pertains to the realm of hours or days, biological processes again hours or days, and then if we go to ecological processes, then the scale are the largest one, when we may talk about months, seasons, years, and so on. These are the scales for the ecological processes. Again, the space in this case for the ecological processes are on the orders of kilometers or tens of kilometers or hundreds of kilometers and so on. Okay. Excuse me, I have to close telephone. Okay. Same description, same analysis of the relationships between spatial and temporal scales. In this case, again, we have physical models that are at the highest resolution in terms of spatial scales and the lowest resolution in terms of temporal scales, and then you go to the ecological models. But between these scales, there are some kind of interactions. So as we have already said, physical models may interact with chemical models, but on its turn may interact with biological models that on their turn interact with the ecological models. This is just to show you that all the scales, or the, if you want, the confining scale have to be taken into account if you want to make a solid description of your ecosystem. The other point you have to keep in mind is that there may be feedbacks on the various scales that may not always be easy to identify and to describe into your model. This is why the modeling procedure we have introduced up to here is an iterative procedure in which each step you go back to see if your description is consistent or if you need to include some more processes. What are the type of processes that we are going to describe now? Physical processes, so transport processes, or processes of phase change, chemical processes, so reaction, chemical reaction, and chemical equilibrium, and then biological processes. that are primary production, like nutrient cycling or other processes of removing of contaminants like BOD removal and so on. All the final part of this class will be devoted to the description of biological processes. So up to now, this week and the next week, we are going to describe physical and chemical processes. And then starting from the week after, we will start to describe biological processes. That is the real, the truly new part of the story for you. Let's see how we can introduce the first mass balance description. Let's focus on elementary volume of my system. Elementary volume is a small cube describing the ecosystem. You may identify this cube by giving dimension, delta epsilon, delta x, and delta z vertical, delta epsilon, delta x horizontal, and then we shall keep into account, we shall consider the fact that through this elementary volume, there is a flow, an incoming, entering flow, and an going out flow, an exiting flow. Again, we start by employing the energy conservation principle through a continuity equation. So as it is customary, and as we have discussed up to now, we may write that the accumulation inside this elementary volume, accumulation of something, is equal to what goes in minus what goes out from the elementary volume, plus minus what changes through chemical reaction. So you have two terms, an input and output that describe physical transfer, and a third term that describe physical, chemical, and biological transformation that are reaction terms. So physical, typically change of phase, chemical, typically a chemical reaction, and biological processes like primary production or oxygen cycle and so on. The first model that the environmental engineer is thought of is the so-called CSTR model, or continuous stirred tank reactor. In this model, we start by the zero-dimensionally assumption. In this case, we are assuming the system is well mixed and there is turbulent diffusion that dominates. So the zero-dimensionality assumption. So we are describing our system, all the heterogeneity of our ecosystem in one point. We may generalize this approach by introducing a plug flow reactor, which we have processes of advections that dominates. In this case, we are one-dimensional, or we may employ an MFR, so a mixed flow reactor, that is essentially controlled by dispersion and advection. And this is typically what you do when you want to describe estuaries or coastal zones or sea areas. How do we introduce the CSTR model? Again, we start from the accumulation. We start from the continuity equation. Accumulation is equal to input minus output plus minus reaction. Let us imagine that this dewar with a mixer is a completely mixed, so continuously stirred, and is a tank in which there is a reaction. So this is a CSTR. We may imagine that we have a load of something. So a load that is proportional to the discharge Q times the concentration in the input, and an outflow that is the concentration in the outflow. How can we translate this? We may write that accumulation is equal to the volume of the element times the variation in time of the concentration of the substance. The derivative in time of C is equal to the load, what goes in, minus what goes out, the outflows. What goes out is outflow Q, So discharge time concentration minus what it is taken away from the system by settling, so minus the setting velocity times the areas, the surface areas times the concentration. So this is the outflow term. This is the outflow plus settling, and then a reaction term that is represented by minus K times Vc, in which K is the constant of equilibrium of a chemical reaction. So K times the volume times the concentration. And if we look for a solution of this equation, now you should be confident with that. This is a first order linear differential equation. First order because we have only first derivative, linear because there is only a linear dependence on the variable C, concentration. Then we may find a solution of this order, and as you know, the solution is the exponential, decreasing exponential, so you may write that the concentration, the outflow of a CSTR system is equal to the concentration in input times a negative exponential, a decreasing exponential, whose decreasing coefficient is lambda, plus a particular solution, but depends on the load function and on the initial conditions. Then the lambda, that is describing the decreasing concentration, is dependent on the discharge times on the settling parameter times a constant K that is describing reaction terms or transformations. Let's see some examples of what happens for different load functions. In the case of the CSTR model, let's assume a Dirac load function. This means that we have a load event that is a pulse, a mass that is transferred instantaneously at time t0. This function, this is the delta of Dirac, which is equal to 1 when t is equal to t0 and equal to 0 elsewhere. This means that the load function is equal to m at time equal to t0. In this case, the solution of this differential equation that we have calculated analytically, because this is a first order linear, so simple, we can have analytic solution. So the solution of this is that the concentration is equal to the mass divided by the volume multiplied a decreasing exponential factor. In this case, for the case of pulse function, let's see what happens if we put some values, the parameters that appear in the model. For example, for different values of the load function, different values of the settling velocity, different values of the settling area, different values of the discharge, different values, of the volumes of the settling velocity, and different values of the chemical reaction terms. In this case, you have decreasing curves, which very quickly, as time passes, I recall you, this is the concentration in the outflow from your CSTR system. The concentration in the outflow is exponentially decreasing. This means that very quickly, depending on the various values of the parameters, more or less quickly, the concentration in the outflow of the CSTR tends to 0. Let's see a different situation. The situation, for example, this situation, the pulse represents somebody that goes into your river system and instantaneously discharges a certain quantity of toxic material. And the effect is but as time passes, this is what once was called purification by dilution. This means that as time passes, the concentration decreases exponentially at different speeds, at different rates, depending on the characteristic of a system. Differently, it happens if, for example, you consider a step load function presented by a step. This means, for example, that somebody at a certain point builds a discharge or builds a sewage system that brings polluted water pollutants into your water body. In this case, what it happens, the solution, as we have modeled by the CSTR, is this one. Concentration depends again on the load function, the volume, and exponential decreasing coefficient. In this case, we have a kind of saturation behavior in which the purification by dilution stops after the plafond is reached. So what's going on here is that you have a discharge of a toxic substance that happens at a certain point and then remains constant in time, and your water body lowers the values of a saturation concentration in time and depending on the characteristic of the system. And then we may see another interesting example with we have an instantaneous load of a toxic substance, and then the load stops. So we have this shape for the load function. Here we start discharging, and then there is a decrease in the load. In this case, the water body tends to lower the concentration of the toxic substances in time more or less rapidly according to the characteristic of the systems we are considering. Please note that the CSTR approximation is a powerful approximation because it allows you to find this kind of description of what happens with concentration in the water body, and this kind of description is very useful for managers. So these are very simple models that allows you to forecast the situation in the immediate future. And you may employ the CSTR approximation even for describing more complex systems. For example, you may subdivide your systems in areas, volumes, in which you may assume valid the CSTR approximation. So you may employ networks of CSTR. You may employ this paradigm to describe arbitrary complex system, even 2D or 3D system. For example, you may build this kind of networks. I can give you an example, for example, what we have published in 2005, in which we have made an evaluation of the effect of the discharge of a large river. In particular, this is the Po River system that is discharging in Northern Adriatic Sea. And then we have simulated the Northern Adriatic Sea by employing a network of CSTR. We have employed two layers for the vertical heterogeneity and a set of boxes for the horizontal heterogeneity. And we have described the model by estimating the flow through these different CSTR boxes. This is just to give you an idea of how you can employ this kind of approach to describe also complex systems. Then we shall finish with PFR. In the case of PFR, again start by describing my system by unit of elementary volume boxes. In this case, again, PFR, so we have a main dominating flow. In this case, you may again rewrite the continuity equation. How do you formalize accumulation? Accumulation is what goes in minus what goes out, minus, let's say what is transformed to chemical reactions. In this case, you may explicitate the inflow in the elementary volume by writing, but the quantity of material entering into the elementary volume J in is equal to the speed of flow times the concentration, and the speed of flow may be simply calculated as the discharge divided by the area through which this flow happens, and J out is simply equal to what goes in plus a variation element that depends on the derivative in times how much the concentration changes along the main direction of flow, in this case x, the flow in x. In this case, if we put this together, we obtain a mixed derivative differential equation in which we write that the variation in time of the concentration C is equal to the variation of the concentration along the main flow axis times the speed of the flow minus what is transformed due to chemical transformation. In the steady state, so in the state in which the dC is equal to 0, dC over dt is equal to 0, so we do not have variation in the concentration. In this case, the solution is again a decreasing exponential. Sorry, MFR, PFR. We have a decreasing exponential. But depends on the horizontal position x and on the speed of the flow and on the rate of chemical transformation. In the case of a mixed flow reactor, that is, in case in which turbulent transport dominates, this is typical for rivers. How do you rewrite this? You rewrite this by estimating the flow, the inflow into the elementary volume as depending on the concentration times the speed of the flow minus the coefficient, that is the eddy diffusion coefficient, describing how the concentration varies due to eddy movements. So the dependence along the x-axis, for example, in one dimension, is this one. In this case, you put all this together, and in a steady state, the C over dt is equal to 0. You obtain this equation, but is not anymore a first order. Instead, it is a second order differential equation, partial derivatives, which you have derivatives in space, in this case, second order derivatives. And what you obtain for the MFR reactor, mixed flow reactor, you obtain this kind of model that is a second order derivative model, which is a differential equation of the second order in the variable x, one dimensional and three dimensional. We will see tomorrow, sorry, on next Thursday, what happens in three dimensions. And we will introduce advection and dispersion, that are the models employed for mass transport in three dimensions. Okay, I stop here today and I rest into the class for some minutes. If you have any doubts, or if you want to ask something, I'm here for answering your doubts. Otherwise, stop.